So our next speaker is Professor Miranda, currently president of Colorado State University, but a long time friend. Yesterday at dinner, we realized that I know him before I knew anybody at the dinner. So thank you very much for coming.
Well, it's a great pleasure to be here. Thank you for the invitation. I'm going to report on some joint work with Ciro Ciliberto, University of Rome, and Kim Roy at the Universidad Autónoma de Barcelona that we did last year. It will not be so beautiful. I think that the main beautiful part of the talk will be the fact that the slides are more or less like a golden rectangle shape. That's about all I can do. So I want to talk about the outline of the talk will be sort of basic definitions, and then I'll remind you of three conjectures that have to deal with interpolation that are famous. Then I'll go into the theory, a little bit of the Mori theory, then make a few more recent conjectures, and then end with results that we discovered last year. And so this is the general setup. So you take C2, take the complex plane, fix some general points, n general points, and fix for each point you choose an integer, mi, and you ask for a polynomial of a certain degree in two variables that has multiplicity mi at pi, okay? And to have multiplicity m at the point means that not only it vanishes, all the partial derivatives up to order m minus 1 vanish. So if m is 1, that means that it just passes through the point. If m is 2, then both linear derivatives pass through, are 0 as well, so you have a double point, etc. And so the question you can ask, if you fix the points and fix these multiplicity conditions, what is the dimension of the space of such polynomials that do this? Okay, and this is not known in general. So for a general number of points, it's known for small numbers of points, it's known for small degrees, but it's not known what the dimension of this vector space is. These are linear conditions. So you get a vector space. It's not even known what the lowest degree is for which there exists a polynomial. Never mind the general question of the dimension of the vector space. And we usually, instead of working in the affine plane, usually work in the projective plane to get the same questions. Because the points are general, you can avoid any line you want and consider them in the affine plane. So some naive dimension counts. If you look at just the number of monomials you have, it's d plus 1 times d plus 2 over 2. This is the number of monomials of degree d or less. So that this is the dimension of the vector space of all the polynomials you have to work with. If you ask for a point of multiplicity m, you're asking for m times m plus 1 over 2 derivatives to vanish in a number of conditions. So if you have more monomials, if you have more dimension in your space than you have conditions, of course you're going to get solutions, right? A non-zero polynomial will exist. So this is, I multiply both sides by 2 here. That is the condition. By the way, I want to, let's see, if I go to this picture here. This is just a cartoon of 3 points. I asked for a multiplicity 1 at one point, multiplicity 2 at another point, multiplicity 3 at another point. You see what the curve might look like. It's a number of multiplicity naively could be the number of branches that pass through the point, right? This is what. So you fix the points, you fix the multiplicity, you ask, is there a curve of degree d that does this kind? Okay, now let's try to organize the information that we're given. So this collection of integers that you have the degree D and the multiplicity numbers can be organized into a vector of integers. And this is essentially the Picard group of the blow-up of the plane at the points, okay? If you take the plane, the ordinary plane P2, the Picard group is just the one-dimensional given by the degree of the line bundles. That's the D part. But for each point you can blow up those points and you get an extra dimension to the Picard group generated by the exceptional curve over each point. And so the Picard group of the blow-up is isomorphic to this data here of the degree and the multiplicities. This is the integer Picard group. You can also tensor with the rational numbers and look at the rational Picard group. Or you can tensor with the real numbers and look at the real Picard group, allowing the degrees and multiplicities to be real numbers instead. Now, this doesn't have necessarily meaning as far as the polynomials go, but we'll see later, we'll see that it organizes the information in an interesting way by looking at the cones. So of course, the ordinary Picard group, the integer Picard group sits inside the rational Picard group, sits inside the real Picard group, which is a vector space. Now, there's an intersection form, of course, that's running around here. It's basically the intersection form on the blow-up, but even without blowing up, you can understand the form if by using Bezout's theorem. If you have two curves of degree D and E, they should meet in the product of the degree number of points, right? A curve of degree 5 and a curve of degree 8 should meet in 40 points, 5 times 8. Now, if, however, you are forcing these curves to have multiplicity at the same point, then they are forced to meet many times at that point. If one curve has multiplicity m and another curve has multiplicity n, then they are forced to meet m times n point, m times n times at that point. So this difference between the number of times they meet totally and the number of times they are forced to meet by the multiplicity conditions is an interesting number. Basically, it's the rest of the intersections, right? The unknown, the ones which are not forced by the multiplicity conditions. This is exactly the intersection form also on the blow-up of the plane at the endpoints. Given that intersection form, that's a quadratic form on the Picard group, you have the self-intersection of a class, d squared minus the sum of the squares of the multiplicities. You have the canonical class on the, this is the anti-canonical. There should be a +3 there, and that's the anti-canonical class. And then you have the intersection with the anti-canonical as well, which are important numbers, as you all know from the Riemann-Roch theory. So this naive dimension count, you see what c squared is, d squared minus the sum of the squares of the multiplicities, and you see what minus ck is, 3d minus the sum of the mi's. If you just go back to this condition here, that a non-zero polynomial exists, if you just look at that, it's d squared plus 3d plus 2 bigger than m squared plus n, sum of the m squared plus n. This is exactly this condition here, that c squared minus ck should be big enough. In fact, bigger than -2. If that's bigger than -2, then you certainly have a curve exists because you have more monomials than you have conditions. This quantity c squared minus ck is always an even number. So that's a naive conjecture you could make. Well, if there's a curve exists, this is certainly true. Is this necessary and sufficient? It's not. So let's try to understand why. One reason why is that suppose you look at what's called a -1 curve. So a -1 curve is an irreducible curve on the blow-up, which has the square self-intersection is -1 and the intersection with the canonical is -1. Okay. So example would be a line through 2 points. So if you look at the self-intersection of a curve of degree 1 with 2 points of multiplicity 1, that's a line that's forced to pass through 2 points. That's a -1 curve. A conic through 5 points. A curve of degree 2, which is forced to pass through 5 general points, is also a -1 curve if you look at the formulas for the square and the intersection with the canonical. Now, if you look at numerically, this condition that we had before, that if c squared minus ck was bigger than -2, the curve should exist. This -1 curves, e squared minus ek is 0, which is bigger than -2. So the curve certainly will exist. Okay. Numerically, if you have a numerical -1 curve, you will have a curve. Now look at the double of the curve. Okay, just take the parameters and multiply the degree by 2 and all the multiplicities by 2. Okay. Then, well, it's a quadratic form. So if e squared is -1, then the double when you square it is -4. And if ek is -1, then the double times k will be -2. It doubles, right? So therefore, when you look at c squared minus ck, you get exactly the boundary case -2. And so the naive dimension count should say, well, the curve should not exist, right? It's exactly the -2, which means that you exactly have the same number of linear conditions as you have the dimension of the vector space. And so you don't expect, you expect that the only solution is the identically 0 polynomial. Of course, the curve does exist. You have E exists, so whatever the polynomial that describes E, its square describes 2E. Right? And so certainly the polynomial exists, but it should not, okay, according to the dimension count. Okay, so let's return to the, what is the expected dimension of these things. Again, using Riemann Roch, we take we call the virtual dimension the difference between the number of monomials and the number of conditions. Okay, that's, as I explained, c squared minus ck over 2 plus 1. Okay? The expected dimension would be, of course, this virtual number could be negative, right? Impose many singularities. Could be very negative. So you take the maximum with 0. That should be the expected dimension. And the naive conjecture would be that the actual dimension is the expected dimension. Okay? And what the double of the exceptional curve shows that this naive conjecture is false. Right? The 2e, the expected dimension for 2e is 0 because the virtual dimension is 0, but it exists. The actual dimension is 1. Right? There is a polynomial, but namely the square of the equation for E. So the naive conjecture is false. So what are some of the conjectures that are more sophisticated that have a chance of being true? So the first conjecture was made, I think, in the 30s by Segre. Said, look, if you have an irreducible polynomial that satisfies the conditions, okay, then the dimension is the expected dimension. Now, this doesn't violate the double of the exceptional curve example, because the double of the exceptional curve example is not an irreducible polynomial; it's the square of a polynomial. Right? So that is forbidden by the hypothesis, and Segre's conjecture is still not known for if the number of points is 10 or more. A refinement has been developed the last 30, 40 years or so, namely that this example of the -1 curve spoiling the naive conjecture is basically the only thing that can go wrong. Okay, so to be precise, suppose the dimension is bigger than it should be. bigger than the expected dimension. Okay. Then there's a minus 1 curve, which spoils it. Okay. This condition that C dot E is less than or equal to -2 exactly implies that if G is the equation of this -1 curve, then G squared is a factor of every polynomial. Okay, so you have this phenomenon of the square of the polynomials, a square of the -1 curve polynomial being in it. This Segre, Harborn, Hershowitz conjecture, which began to coalesce in the 80s, is also not known for number of points 10 or more. Now, the next conjecture I wanted to mention was Nagata's conjecture. So Nagata in the late 50s, or was it in the 60s? It was in the late 50s. His approach to the providing a counterexample to Hilbert's 14th problem about the finite generation of the ring of invariance of the group actions. He made the following conjecture. Suppose you have 10 or more points, and you have this equation that the square root of n times the degree is less than or equal to the sum of the multiplicities. So this is in some sense some constraint on the degree. If the degree is too small, then the conclusion of Nagata's conjecture would be there are no polynomials. Okay? Constraint. And there's a refinement when n equals 9. Okay? Now, Nagata proved his conjecture for all perfect squares, at least 9. So 9, 16, 25 number of points. But is not known for any non-square number bigger than 9. Nagata's conjecture. So even this little linear condition, which looks pretty harmless, not known. So here are 3 conjectures. The Segre conjecture made in the 30s says that if you have an irreducible polynomial, then you're in good shape. There's the Segre, Harborn, Hershowitz conjecture that says the failure of having the expected dimension is due to -1 curves. And you have Nagata's conjecture, which gives at least one inequality that must be satisfied in order to have curves. Okay. All right, let's switch to thinking more about the entire totality of the space of solutions to this problem, rather than asking a question about a single degree and multiplicity set. So take the Picard group, which is the integer lattice. You have the rational lattice and rational vector space and the real vector space. Array in the real vector space is all non-negative multiples of a vector. Okay, and the array is called rational if it can be generated by a rational vector or an integer vector. All non-negative multiples of a rational vector. For example, the Nagata array, okay, is the one generated by the square root of n and all ones, right? This, if you take the intersection with the Nagata array, that's exactly the condition that this condition, the square root of n times the degree less or equal to the sum of the multiplicities. That's exactly saying that the intersection with the Nagata array is less than or equal to 0. Okay? The Nagata array is the square root of n 1, 1, 1 point. You also have that's for n not a square. This is an irrational array. You have the anti-canonical array, which is generated by cubic polynomials passing through endpoints. And you have -1 rays, right? But generated by a -1 curve. Now, if you have a ray, okay, all you know is the ray, then you don't know what the degree or the multiplicities are. Those things don't make sense because you take any multiple. But whether or not the degree is positive does make sense because you only take positive multiples. And whether or not the square is positive or not, that's also makes sense for array. So you can say the degree and the self-intersection being positive, negative, 0 makes sense for array, an entire array. which is important, you'll see. Now, suppose you have an integer class, okay? So degrees and multiplicities that are all integers. We say that the class is effective if you have a polynomial. There's a curve of that degree with those multiplicities, okay? You have a non-zero polynomial. Now, what does it mean to say a rational class is effective? Well, it means that some multiple is effective. When you clear the denominators, some integer multiple is effective. And so that's the definition of a rational class being effective, and the rational array is effective if it can be generated by an effective rational or integer class. Now, the sum of two effective classes is effective, right? Because if you have a polynomial that exists for one and another polynomial for the other, then the product of the two polynomials has the sum of parameters, sum of the degrees and the sum of the multiplicities. So in general, the set of effective classes forms a cone, right? Closed under sums. Now, what Riemann-Roch says is that if you have a rational class, so of course Riemann-Roch only applies to rational and integer things. If the degree is positive and the square is positive, then it's an effective ray. It generates an effective ray because some multiple would be effective by the Riemann-Roch theorem. So these are the degree and the square will give you some effective classes. And so the question is, what else can you get? So these things, as I mentioned, because of this closed under sums, you have cones. You have the effective cone. Take all of the effective classes for which there are the cone generated by the effective classes, the effective rays. Okay? And because the sum of any two rational rays is effective, it is also effective. These form a convex cone. This is sort of the cone we really want to understand. Right? Which degrees and multiplicities have a polynomial? Right? We'd really like to understand the effective cone of curves. The Mori cone is the closure of this cone. Okay? This effective cone may not be closed. Right? And the Mori cone is the closure. So you may have things at the boundary of the effective cone. You may have limits of effective things which are not effective. So the arrays, you say, well, I mean, if I have a polynomial, then I'll have a polynomial in the limit. Not necessarily, because the ray, you may have to take higher and higher multiples in order to get an integer class as you go to the boundary of the effective cone. And so the limit doesn't really exist because you're having the degree go to infinity. So you really can't generate it. There's no integer limit in the boundary. Now, so you have the effective cone, which you're really interested in. The Mori cone is the closure. And you also have the Nef cone. So a class or array is Nef if it intersects all of the curves, positive, non-negative. Okay. And so you also, this is also a property which is closed under sum. So you have the Nef cone as well. And because this is a closed cone, this inequalities C dot D is bigger than or equal to 0. It's the dual of the closure of the Mori cone. The dual of the closure of the effective cone, which is the Mori cone. So the Nef cone is the dual of the Mori cone, and they're both closed. The effective cone, as I said, may not be closed. And then finally, you have two more additional cones. The non-negative cone is the cone that I mentioned earlier, the classes which have positive degree and positive self-intersection, or at least non-negative. So by Riemann-Roch, the interior of that cone is certainly part of the effective cone. These are things with positive degree and strictly positive self-intersection. Then you have the ample cone, which is the interior of the Nef cone by the Kleiman-Nakai criterion. You have, if a class intersects all of the curves strictly positively and has strictly positive self-intersection, it's ample. Okay, so the ample cone is the interior of that Nef cone. We won't need the ample cone much in what's what's to come. So that you have the effective cone, its closure is the Mori cone, the dual of the Mori cone is the Neff cone, and then you have this non-negative cone related to the quadratic form, the self-intersection. Okay, now what does Mori's cone theorem say, which will give some insight into the situation? So you look at the parts of the cones which are intersect the canonical positively or intersect the canonical negatively. So intersecting the canonical, that's a linear condition and divides the whole space into two halves, the part that intersects positively, the part that intersects negatively. And so take the Mori cone, which is the closure of the effective cone, and it breaks into the part that intersects positively and the part that intersects negatively. Okay, and so clearly the whole Mori cone is the sum of, if you take a cone and intersect it with a half space, it's a cone too. So Mori cone splits into its positive part and the negative part, and it's the sum of those two cones. Now, any -1 curve is in the negative part of the Mori cone because it intersects k minus e dot k is -1, so it's the negative part of the Mori cone. And what the Mori's cone theorem says is that the negative part of the Mori cone is sort of generated by these -1 curves, that the Mori cone itself is the mysterious part that's positive, intersects k positively, and the cone generated by -1 curves, okay? All of which lie on the negative part of the Mori cone. Okay? So the negative part of the Mori cone is well understood related to -1 curve. Not that we understand -1 curves extremely well, but they lie over there, and if you can understand them, you'll understand the negative part. And so the mysterious part is the positive part of them. Moreover, these -1 curves, they could be complicated. Their topology could be complicated, but they can only accumulate on the boundary where the intersection with k is 0. So they can be sort of complicated, even fractal in nature, but they can only have accumulation points on the boundary. They're away from the boundary, they're polyhedral in nature. It's a very useful point of view for this business. So, the conjectures that I mentioned, Segre and SGHH and the Nagata conjecture, they were all conjectures about 10 or more points, remember? So what's going on with 9 or fewer points? Why do we know? We know more about there. We have theorems. And the reason why we have theorems from the point of view of the Mori theory is that things are essentially polyhedral. Okay? So if n is less than or equal to 8, then the anticanonical is ample. So the effective cone lies inside the things that meet canonical class negatively. So the whole Mori cone is inside the things that meet the canonical class in the negative part. The positive part is empty, okay? And so you have a polyhedral, is a rational polyhedral cone. And so the understanding of the effective cone is equivalent to understanding the -1 curves. And these are understanding the -1 curves on Del Pezzo surfaces very well understood for many decades. If n is 9, okay, there could be infinitely many -1 curves. And generally, there are infinitely many -1 curves, but they all accumulate to the boundary, and the boundary only has that one curve in it, minus k, the cubic through 9 points. Okay? And so the Mori cone consists of that one ray, the anticanonical ray, plus the -1 curve. So that's a little more complicated, but not still sort of has very much a polyhedral nature to it. So it's when n is bigger than or equal to 10 is when things start to get interesting. You have things on the positive side of the Mori cone, which is the mysterious non-1 curve part. So recall that a divisor is Neff, class is Nef if it intersects all the curves non-negative. So Nagata's conjecture was exactly that the square root of n times d minus the sum of the mi's would be non-negative if n is 10 or more. This exactly says that this Nagata ray is Nef, right? Exactly says that it's Nef. Now note that the square of the Nagata ray is 0. If I take d squared minus the sum of the mi's, there's n ones there, so d squared is n minus n is 0, right? And n dot k is this quantity, 3 root n plus n, which is positive if n is 10 or more. So we have that the Nagata ray lies in the positive side of the half space. Okay, so these let's go back and sort of reminder. So we have all these interesting cones. The effective cone is the one we really want to know about. Closure is the Mori cone. The dual is the Nef cone. We have the non-negative cone of the self-intersection cone. We also have in every one of these cones, you can look at the positive part and the negative part depending on how it intersects K. And all these cones are unions of rays. Well, one way of understanding cones is to understand the extremal rays. So an extremal ray for a cone is not just a cone that's on the boundary, but it's a cone, it's a ray that's not in the sum of two other rays. Okay, so it's like a corner of some sort, right? Now you can be on the boundary but not be extremal. So if you have a polyhedral cone, then if you're in the interior of a face, you're on the boundary, but you're also in the sum of the two cones, the two rays that form the boundary. Right? So those are not extremal rays. The extremal rays are really the vertices. Okay? If you have a polyhedral cone. If the cone is sort of round in some way, then every point would be extreme. Right? So the understanding of extremal rays is also interesting from this point of view. Now, we have a lemma that I want to expose here. It's not hard to prove, but it does use some Zariski decomposition machinery. I will try to prove it for you today. And it's used to probe the boundaries of these cones. So suppose this lemma says the following. This is the Nefness Lemma. Suppose you have a ray, which is a rational ray. So this is an integer vector in that ray somewhere. Its square is 0, so it's on the boundary of the Q cone, and it's not effective. Okay? Then it's Nef. It's on the boundary of the Mori cone, it's on the boundary of the effective cone, and it's an extremal ray. Okay? Cannot be written. And it's on the positive part of K as well. This is very useful for probing the boundary of the Mori cone and the effective cone. Okay? Find rational classes, so find actual integers, d and mi, with the square 0 condition, so d squared equals the sum of the mi squareds, such that it's not an effective ray. So not only is there no curve with that d and mi, but no multiples either. So no multiple of those parameters have a curve in it, okay? Or have a polynomial that satisfies the condition. If you can prove that, then you found an extremal ray for the Mori cone. Okay, so we're going to use this terminology of good and wonderful. So we'll call this situation a good ray. If it's rational, it's not effective, and the square is 0. It's exactly the hypothesis of the Nefness Lemma. And the Nefness Lemma says if it's a good ray, then it's extreme. Okay? And it's difficult to prove that a ray is good. Okay? You have to show that the primitive so every rational ray has a primitive vector, the sort of smallest integer vector in the ray. That primitive integral vector and all multiples are not effective. There's never any curve. No polynomial exists. So this is not so easy to prove usually, because you're right at the boundary of the situation where it should exist or not, according to Rimmeron. Now we're going to introduce terminology. A wonderful ray is an irrational ray with square zero, which is Nef. Okay, so it's also going to be at the boundary. Okay, but it's irrational. So these are very mysterious objects. It's an irrational thing at the boundary. It should be an irrational limit of good rays. Okay, they're also extremal. Okay? These limits. So they'll be very interesting to find. And they would be, if you have an irrational ray, if you have one wonderful ray, they would be evidence that the Mori cone does not have a polyhedral nature, but it somehow has a round nature around an irrational ray. Say it again. Yes, I will. Yes. That's the whole point of the talk. So we have a couple of more conjectures now. What we call, this is a conjecture made by Giliberto, Brian Harborn, me and Kim Roy about, I don't know, 6-7 years ago, that the Mori cone in this range of n bigger than or equal to 10, the Mori cone was the positive part of the non-negative cone, the Q cone, plus the exceptions. This could be true. We don't know if it's true or not. But this would be kind of the easiest thing that could be true. I mean, very, very rather simple statement.
Do I understand correctly that this is like a special thing for these blocks?
At general points.
At general points.
Yes. 10 or more. Okay, there's one more ray that turns out to be interesting. And you mentioned de Fernex earlier. The de Fernex ray is just a little different than the Nagata ray. The Nagata ray had the square root of n and then all ones. The de Fernex ray is just a little over from the Nagata ray, square root of n minus 1. And the conjecture made by de Fernex and also related to this delta conjecture is that for n strictly bigger than 10, there's also a version when n is 10, but that's a little more technical. If you have a rational ray, square zero, and its intersection with the de Fernex ray is less than or equal to 0, then it's not effective. Therefore, it's a good ray, and it's a Nef ray, and it's an extremal, etc. If it's irrational, square 0 and intersects de Fernex negatively, then it's Nef, and hence is wonderful. Okay, so this would be rather simple ways related to the delta conjecture to extract information about the boundary of the Mori cone. These conjectures would imply the Nagata conjecture, and the Nagata conjecture in this range bigger than 10 points does meet the de Fernex ray negatively, is irrational, hence would be Nef, according to this. So these conjectures are stronger than the Nagata conjecture. Okay. By the way, any good ray or any wonderful ray would provide counterexamples to the Hilbert's 14th problem in the same following Nagata's proof word for word, more or less. It's the same technique we showed. So many, many examples if you can find good rays or wonderful rays. Okay, so can we find some? And they're difficult to find, but not impossible. And about 5-6 years ago, we found in the same paper where we made the delta conjecture, we proved that good rays exist for any n bigger than or equal to 10. This was the first time this was observed. The proof was constructive. We actually wrote down for every n bigger than or equal to 10 some good rays using the Nefness Lemma. Okay, so the Nefness lemma says you have to prove that a square zero array is not effective. Right? That means no multiple is effective, no multiple of the primitive, which means you have to prove, many, an infinite set of theorems that there are no polynomials for any multiple of the parameters. And we use the degeneration argument, which we had developed back in the 90s, 2000s, to show this. An example, there are no curves of degree 13 with a point of multiplicity 5 and 9 points of multiplicity 4. Or any multiples of those parameters. There's no curves. So it seems like a rather simple statement. If you work out the numbers, it's exactly the expected dimension is 0. So for this, you should not have such a curve, but the fact that you should not doesn't mean that you don't. Now, last year, Chiro and I constructed many more families of good rays, rational rays, which we proved were square zero and no multiple is effective. Okay? And this, it gave us a little more insight into what the Mori cone is using the Nefness Lemma. But no wonderful rays were known until this year. I want to explain a little bit at the end of the talk now how we constructed some wonderful rays. So the result that we proved last fall was that for all n bigger than or equal to 10, wonderful rays exist at the boundary of the positive part of the Mori cone, where k is 0. Okay. When n is 13 or more, we were able to construct for every n wonderful rays on the strictly positive part. The hard part to understand. And then for these special situations, 14 and any n such that n minus 4 is a square or n minus 2 is a square if you're bigger than 18, we have wonderful rays which intersect the de Vernix ray, strictly negative. So for example, so you asked for a specific example. The proof was constructive. I mean, we didn't write down. So if you take the degree equals to 1428, very high degree, and the first 4 multiplicities are this number, 21 times 15 plus beta. So beta is the square root of 21. And the next 7 multiplicities are 462 minus 5 beta. And the last 2 multiplicities are 14 times 15 plus beta. This is a wonderful ray. Okay, clearly, it's an irrational ray. And we proved it was a limit of good rays. Now, how do we do this? Before I tell you how we do it, maybe I'll switch to this other picture. You see, this is how a cartoon of the Mori cone. You see the Q part, this sort of blue curved parabola, looks like I think it's a hyperbola. That's the positive cone. Okay, so to the right is Q is positive outside that, and then we have these 3 linear conditions with k is 0. On the right is where k is negative, and the left is where k is positive. So that's the mysterious part of where k is negative. Then you have the de Vernix ray, where intersection with the de Vernix ray is positive, is 0, and then you have the Nagata, where the intersection with the Nagata ray is positive, is 0. Right? And in the 3 points I've indicated, you have the Nagata ray, the de Vernix ray, and the anticanonical ray. The -1 curves are over on the right? There's places where the intersection with the canonical is negative. And so what de Vernix is saying is that the Cone Theorem says that whatever happens on the left side plus the -1 curves on the right side is the Mori cone. Right? What de Vernix says is that is more precise. It says that on the left side, the Mori cone, the Q positive stuff inside the hyperbola, but on the left of the D equals 0, so intersecting D negatively, okay? That's the part of the Mori cone that's intersects D negatively. Then it gets mysterious in between the D equals 0 and the K equals 0. That could be influenced by the other stuff, and then the -1 things. And then you have the -1 stuff. So this is a little cartoon about how you might visualize this cone behavior. All right, what was the way we proved this example? So the proof, we started with a good ray. And remember that 5 years ago, we started having the ability to generate good rays. So we had some technology for good rays. So what we did was we took a good ray and used a Cremona transformation to transform it. When you transform a good ray, Cremona transform is still good. Parameters are preserved. So this is represented when you apply the Cremona transformation to a class, it's a matrix, right? It's an n+1 by n+1 matrix. It changes the degrees and the multiplicities in a prescribed way. And so you can iterate this, this construction and apply Cremona over and over again. When you do this, the ray has a limit, okay? That corresponds to the dominant eigenvalue of this matrix A, that is the Cremona matrix, okay? And it turns out the dominant eigenvalue is irrational. It's the root of a polynomial of degree n+1, so it might be irrational, and it is. And the eigenvector then is irrational, and that eigenvector is the limit of the Cremona. Now that limit lies in the k equals 0 part, unfortunately, but it gives these wonderful rays with k equals 0. Now, if you want to jump into the positive part, you have to work a little harder. So what you do is you take, you can take 4 points, four points and collide them together to get 1 point, okay? And this produces systems which collide to these Cremona images, and the limit of those systems then, which I mean, you're replacing 1 point by 4, right? So you go from 10 points to 13 points or more. That's why the wonderful rays require 13. And since the collided system was not effective, before you collide cannot be effective either by semi-continuity. So those TKs can converge to also the desired wonderful rays, but they have different linear properties and meet the different X-ray negatively and the canonical negatively or positively. So that was the technique. We used the Cremona transformations, take a limit of Cremona transformations, and then uncollide one of the points to 4 points of smaller multiplicity. Now, one additional thing. So in this way, I showed you an example. We got one single ray out of this technique. Just over the winter, just last February, we not only found these isolated wonderful rays, but we were able to, in the 13 case, we were able to find a one-dimensional arc at the boundary of the Mori cone consisting all of good rays, okay? And in that arc, there are, of course, many irrational points in that arc. So here's a further evidence that for the delta conjecture, that the positive part of the Mori cone is generated by the Q equals 0 thing. And that arc was all in the different X negative range too. So here, with that, I'll close. That's the results so far. Stay tuned. We're looking for more wonderful rays all the time. We hope to expand our understanding by creating higher and higher dimensional patches of this boundary of the Mori cone, and maybe in the limit we can prove this delta conjecture that the Mori cone is generated by the positive, by the Q, on the positive part by Q and on the negative part by the -1 curves. Thanks very much.
Wonderful talk. Any questions?
The Nefness ray, and yeah, it's a little technical how the Nefness ray gets involved. And I'm not really Nefness's argument about why the delta conjecture would imply this Nefness conjecture, that the Nefness ray kind of defines the boundary between the Mori cone being defined certainly by the Q cone, then in between the D = 0 and the K = 0 space, it's also mysterious near the boundary. And then over on the other side is -1 curve. What can happen is on the -1 curves can be kind of high up in that region. And so when you take the sum of the two cones, you're connecting points on the positive part with -1 curves, and you can imagine that it shaves off a little bit and penetrates outside the Q cone. Okay, what the Nefness proved is that can only happen rather close to the K = 0 part. It can't happen if you're on the other side of the Nefness. That's
So in the beginning, you were saying something about the dimensions. So, I mean, then it was just like, is it 0 or not 0?
Yeah, all of this is whether or not it's 0 or not. This doesn't speak to the dimension problem. No. The conjecture is that if there is no -1 curve that spoils, then the dimension is equal to the expected. That's the Segre, Gimigliano, Harburger, Schumann's conjecture.
Thank you very much. Okay, one moment to change the